Cool.
There we go.
Okay. Thank you. Wouldn't be the first time I forgot, as you know. All right. So what I want to talk about are some units associated with compounds and atoms. Now, there are some units that you'll hear frequently and some that are more obscure. One is called atomic mass, and that is the mass of a single atom of a particular element. And it's based upon the mass of one carbon-12 atom. So hydrogen, for example, is 1.01 atomic mass units, AMUs, or just plain U's. 12.01 for carbon. And it depends upon the isotope also. Now, usually we don't use atomic mass and formula mass very much. What we normally use is molar mass. Now, there's atomic mass and formula mass. Formula mass is the sum of the mass of all the atoms in a chemical. Atomic mass is the mass of a single atom. Okay, so formula mass is made up of atomic masses. And again, formula mass is the unit is AMU, atomic mass unit, or plain U. Now, molar mass is usually what we use when we're doing calculations, because the atoms and molecules are so incredibly small that it's not useful to talk in terms of a single molecule or a single atom. So what we do is we mass them together in a very large unit called the mole. And the mole is 602 times 23, that's 10 to the 23rd, atoms or molecules. And it's just a number, it's like a dozen. How many are in a dozen? 12. Doesn't matter if we're talking about atoms, molecules, or ducks. Doesn't matter. Moles is just a number, and it's convenient. It conveniently conveniently large because atoms are so small. Okay, so the smaller the unit, or excuse me, back up. The smaller the item, the bigger the unit. Now, a dozen is usually we're talking about eggs or something like that. An egg is pretty good size compared to an atom or molecule. Atom or molecules are incredibly small, so the unit is a very, very large number. 602 times 10 to the 23rd is a really huge number. That is 6 with 21 zeros after it. It's a big number. Okay, so the molar mass is based on 6.02 times 10 to the 23rd atoms or molecules of the chemical. So if we add up all the atoms in terms of their molar mass, we will get the molar mass of the molecule. As an example, water. If we look on the periodic table here, you'll see hydrogen is 101, oxygen is 16. So the molar mass for water is so that's 1802 grams per mole. Now you can abbreviate mole as MOL if you would like. It's not much of an abbreviation, but okay, so that's molar mass, and it's used most of the time. But you need to understand the difference between formula mass and atomic mass. So atomic mass is the mass in atomic mass units of a single atom. Formula mass is the mass of all the atoms in the chemical. Okay, but we're talking about one molecule now, and that's also in AMUs. Okay, for example, the formula mass for water would be AMUs or U's. So you can substitute in AMUs, grams, or U's. Okay, so let's do a couple review problems from last time. And remember, we're going to be using dimensional analysis the whole semester. Okay, so what's the mass in grams of 2.49 times 10 to the 45th molecules of white table sugar? That's the formula for table sugar. Okay, basically table sugar is a molecule of glucose and fructose attached together through a glycosylic linkage. Okay, so we're starting with what's given is molecules. And let's just call this sugar. We're trying to calculate grams. Okay, so is there a conversion factor to go directly from molecules to grams? No, we're gonna have to go through moles. Moles is always the intermediate, I shouldn't say always, frequently the intermediate conversion that you're gonna be going to. So we want to go from molecules to moles. Now remember, we're going to be using Avogadro's number. And this is Avogadro's number. And guess who discovered this number? Dr. Avogadro. Okay, it's kind of cool. If you ever go to Trader Joe's, sometimes they'll have a Avogadro's dip. It's based on their avocado, and they're very clever on their little cutesy stuff from Trader Joe's. Most of their fruit is pretty good too. Some of it's okay, not great, but okay. So we need to convert the number of molecules here into moles. Now this could be atoms or molecules. In this case, we're talking about a molecule, so it's going to be molecules. Okay, so this gives us moles of sugar. Now we need to go from moles of sugar to grams of sugar. So we need to find the molar mass of sucrose, or white table sugar, okay? So we're talking about 12 carbons at 1201 apiece. We're talking about 11 oxygens at 16. So this is carbon, oxygen, hydrogen is 22 at 101 apiece. So what does that add up to be? We're doing 12 ones. Plus 11 16s. 22 101s. So we're looking at okay, so 342, 34 grams per 1 mole. Okay, so what are we trying to calculate? Grams. What is left over after we cancel everything? Grams. So the setup is correct. Sig fig wise, okay, we have 3 sig figs, 3 sig figs, 5 sig figs. So the answer is going to be 3 sig figs. We're going to multiply 2.49 times 10 to the 45th times 324.34. Divide all that. Excuse me again. Avogadro's number. Okay, so we have going to 3 sig figs. That's 142 times 10 to the 24 grams. That's a big mass. That is a big mass. That is 1 with 22 zeros after it. Big time. $142, but 22 zeros. Okay. All right. Does that setup make sense? I don't know if you've practiced any of these yet.
Yes.
It's strictly dimensional analysis. Okay. Okay, if we start with, again, I'm going to review some of these problems here just to make sure everyone's in the same boat here. How many molecules? 4.56 grams of water. Well, we're starting with grams. We're going to end up with molecules. And again, we need to go through moles as our intermediate conversion. Okay, so water we've already done a little while ago. That's 1802 grams per mole. Does everyone see where the 1802 came from? Molar mass of water. Okay, this gives us moles. Now we're going to go from moles to molecules, again using Avogadro's number. So moles of 80 on the bottom, so it cancels. Avogadro's number. Okay, so we're looking at 3 sig figs, so it's 152 10 to the 23 molecules. And this is water. And that is water. We have 3 sig figs, 4 sig figs, 3 sig figs. So our answer is going to be 3 sig figs. Okay. How many atoms of hydrogen are in 23.12 grams of water? Now I'm talking about atoms, not molecules, atoms of hydrogen. Remember now, here is water. If we have 1 water molecule, how many hydrogen atoms do I have?
Two.
Right. If I have 34 molecules, how many hydrogens do I have?
68.
Yep. Okay, so the ratio is 2 hydrogens per 1 water molecule. Okay, that is a conversion factor. It's a conversion factor. You're going to need that in this. Okay, so we have grams of molecular water. That's what's given. So if we convert that to moles of molecular water, good old 1802 again. This gives us moles of water. We don't want moles of water. We want atoms of hydrogen, okay? Well, we don't have molecules yet, so we need to convert to molecules first, okay? So that's going to be using our Avogadro's number. And this is molecules now. Not atoms, molecules, because the mole is for molecules, not atoms. Okay. Now we have molecules of water. We're going to be using this conversion factor here to convert to atoms of water. Excuse me, atoms of hydrogens in water. Again, this is water, so water needs to be on the bottom. So it cancels, and that needs to be on top. Okay. So molecules cancel. Leaves us with hydrogen atoms. Okay. Does that setup make sense? This is the part, the tricky part. Last part there. Okay, so let's crank this baby up. Okay, so you're gonna multiply everything on the top, divide by everything on the bottom. And then notice we just have one thing on the bottom. Okay, so we're gonna do we're talking about 4 sig figs, 4 sig figs, 3 sig figs. What about this? How many sig figs is this here? How many sig figs is that?
Is it one?
1.
No. If I said how many sig figs is that? 12 eggs over 1 dozen. Remember there were some exceptions when we were talking about sig figs a while back? When we have a definition, it's infinite.
Is that the one where you're still counting them? Okay, yes, infinite.
Yeah. It's like counting, only it's not. It's by definition. We're just saying 12 eggs is exactly 1 dozen, not 12.1. It's not 11.9. It's exactly 12. Same with this over here. It's exactly 2 atoms per 1 molecule. So that's why this is infinite sig figs. So basically, that doesn't come in the picture. Because remember, we're looking at the smallest sig fig. So our answer is going to be 3 sig figs. Now we're going to see the same thing in Unit 5 when we do something called balanced equations. The equations are going to be balanced in terms of coefficients, and it's going to be the same thing again. It's going to be infinite significant figures. Okay, so grinding all that out to 3 sig figs, it's 154, 24 hydrogen atoms. Now, this is frequently missed on tests. And the part that's missed is this last step here. So frequently on tests, their answer will be 0.72 times 10 to the 24th, because they're calculating molecules of water and not hydrogen atoms in the water. So this, and you will have one of these on your tests. So just be careful of this last step, the conversion from atoms to molecules or molecules to atoms, okay? That's the tricky part of this question. Now, this question here is going to be almost the same thing, only we're starting with molecules rather than grams. So this is the same concept, only we're starting with molecules. Okay, so how many hydrogens are per 1 molecule of sugar? This is exactly like the water one. So with water, how many hydrogens were per water molecule?
2.
2. So how many hydrogens are per sugar molecule?
44.
22.
Oh.
Because when you have one C12O11 H22, you take that all apart, you have 22 hydrogens, but you started with 1 molecule of sugar. Okay, is everyone okay with the 22? It's
Yes,
analogously to the water. We have 2 H's per 1 water. Here we have 22 H's per 1 sugar. So we have 2 sugars, we have 44, we have 10 sugars, we have 220. We're just multiplying the number of molecules, in this case, the whole bunch, times the number of hydrogen atoms per 1 molecule of sugar. So that's going to be 547. And we have 3 sig figs, infinite sig figs. Same concept here, because there are exactly 22 hydrogens per 1 molecule of sugar, exactly. So there's nothing measured here. Okay, so it's 547. Actually, it's 548. Rounding to 3 sig figs. Okay, now, when we look at formulas, we've already been looking at formulas in terms of the atoms. You can also look at things like the ratio of one atom to another. Okay, so let's look at water again. We can take and look at the ratio of H's to O's. What is the ratio of H's to O's with water?
2 to 1.
Exactly. So another conversion factor. So whenever we have these fractions, they're always conversion factors. That means we also have the inverse. 1 atom of O per 2 atoms nitrogen. Okay, We can also have mole ratios. So that would be 2 moles each for 1 mole. Oh, with water. Same idea. Now the tricky one is the mass ratio. Now the mass ratio requires you to use the molar mass of the atom or the molecule. So for example, with water, we have okay, and where did they get the 202?
Each hydrogen weighs 1.01 and there's 2 of them.
Yep, you got it. Because the molar mass of hydrogen is 101, and we have 2 of them. So 2 times 101 is 202. So this is 2 times molar mass of hydrogen, and 1 times molar mass of oxygen. So that'll give us a mass ratio. It's crucial that you use the molar mass when you're talking about this. So we can have all these different combinations. For example, we can have the mass ratio of hydrogen to water. And again, molar mass of water, molar mass of hydrogen. And because there are 2 of them, it's twice. So from the formula, we can have all kinds of new conversion factors just from the fact that it's a formula. So let's look at this number 1 here. How many moles of oxygen are 18 moles of carbon dioxide? Okay, we're starting with we want to end up with moles of oxygen. So we want moles oxygen on the top, moles carbon dioxide on the bottom. What's the ratio of oxygen to carbon dioxide? This is just like the water problem. How many O's are in each CO2?
2.
Exactly. 2 to 1. So we have 36 moles of oxygen. This is a similar one. Calcium carbonate. Okay. And we want to know the number of, again, of oxygen. So how many oxygens are per 1 mole of calcium carbonate?
3.
3, exactly. So it's 3 to 1. So 3 times 17 is what? 51. And number 3 is same kind of deal. Okay, so we want 1.4 moles of sulfuric acid, H2SO4. We want H moles, and that would be 2. That's 2.8 moles hydrogen. Now, we get into this problem, we're talking in terms of moles again. Okay, remember this up here, this mass ratio was a molar mass ratio. Molar mass ratio. So in this problems here, we're using the molar masses. Okay, so we're starting with what's I'll have to do these myself. Can you tell? Okay, so we're starting with 15 grams of sodium chloride. I want to know how many grams of sodium are in 15 grams of sodium chloride. Okay, so we're going to be using the molar mass ratios of sodium to sodium chloride. So we're starting with this would be sodium chloride. And we're going to have to convert to moles first because it's a molar ratio, even though we're talking about molar mass, still a molar ratio in sodium chloride. Okay, so first step is convert over to molar mass, moles. And again, this is going to be sodium chloride we're talking about here now. So sodium chloride is going to be 22.99 for sodium. Chloride is 35, 49, 45. So looking at 58.44 grams per mole. Okay, so that gets us to moles of sodium chloride. And how many moles of sodium are in 1 mole of sodium chloride?
1.
Exactly, perfect. Now we have moles of sodium. And now we can go from moles of sodium to grams of sodium via the molar mass. Molar mass sodium. And sodium is 22.99. So moles of sodium cancels, we're left with grams of sodium. Grams of sodium. Okay. And it's for sig figs, so it's going to be so 5.900 grams of sodium. So 4 sig figs, 4 sig figs, infinite sig figs, 4 sig figs, 4 sig figs. And this is going to be a similar one. Only the difference is going to be we're working with chlorine instead of sodium. So we need to get to grams, actually we need to get to moles of sodium chloride. Then we're looking at the ratio of chloride to sodium chloride. And then we're using 45 grams per mole of chloride. And I'm going to erase this Molar mass here if it is officially in the way. So it's basically the same setup. This is going to be 4 sig figs all the way across again for the same reason. So it's going to be that's 4 sig figs. Okay, so let's look at this problem here. Are these examples helping you guys?
Yes.
Okay, is it, am I going fast enough or slow enough? Is it flowing okay?
Good pace for me.
Okay,
Same.
okay, cool. All right. Okay. Carvone is probably a aldehyde. Aldehydes usually are very sweet. It can also be an ester. I'm not sure. I haven't seen this chemical before, but typically spearmint oil typically is on the sweet side, and it's also volatile. So this is probably an ester, or yeah, I would guess it's an ester. Anyway, it doesn't matter. So we want to know the mass of carbon in 55.4 grams of carvone. Okay, so Okay, so this is doing a quick, we have 10 carbons. Two H's and one O, so that's okay, so we have 1201 times 10 plus 14 times 1 plus 16. Okay, so first thing we're going to do is convert to moles, just like we did before. Now we have moles of carbon. Next, we need to figure out how many, what is the ratio of moles of carbon to moles of a molecule of carbon. So for each mole of carbon, how many carbons do we end up getting? So each mole of carbon, how many moles of carbon do I get? What's a subscript on carbon?
Uh, 10.
Yeah, exactly. Okay, so this gives us now moles of carbon. Grams cancel, moles of carbon cancel, leaves us with moles of carbon. Carbon is 1201 grams per 1 mole. So we have 55.4 divided by 150. Okay, so we have 3 sig figs, 5 sig figs, infinite sig figs, 4 sig figs. So our answer is going to be 3 sig figs. So it's going to be 3.69 grams of carbon. Okay. So sometimes they want to know percent composition of an element. Okay, now, real quickly, percent means fraction. Times 100. Okay, and it's a fraction usually of the whole, but not necessarily. In this case, it's going to be a fraction of the whole. Okay. So, we want percentage of F in CaF2. Okay, so it's going to be the molar mass of the fluorine over the molar mass of calcium fluoride. Okay, so the molar mass of fluorine is 1900. And there are two of them. Calcium fluoride, and calcium is calcium is 4008. Fluoride is 19, so that's what, 1919, what, 38? So that is 7808 grams per mole. And this is all times 100. Now, the units of percent are none. So that means our grams per mole and grams per mole have to cancel because we need no units in our answer. So we're looking at 19 times 2 divided by 78. 100 is 48. Let's see, 4 sig figs. We're looking at 4867. Well, if 48.67 is fluoride, the difference, the remainder from 100 is going to be the calcium. So that's of course, 100 is perfect, so that's 0.0000. So we're looking at for 2 there. That's going to be something for calcium. Okay, so we're looking at percent of mass. You have to use the molar mass. Okay, how many grams of fluorine are in 216 grams? There's a couple ways to do this one. We already know the percent. So we can just do 48% times, excuse me, the 260. I'm gonna have to end this. Finish with this unit here. Okay, or we could grind this out from the beginning, but we've already calculated the percent fluorine. So it's going to be, this is fluorine times remember now, this is a percentage by mass. So that's why we can do percentage mass. So we multiply 0.4867 after convert the percent to decimal. Gosh, excuse me. I think the mole is kicked up. Gosh. Okay, so we're looking at 105 grams. Now, number 3 is kind of an interesting problem. It says FDA recommends adults consume less than 2.4 grams of sodium per day. Actually, you should be consuming a lot less than that, but anyway. How many grams of sodium chloride can you consume still be within the limit? Okay, so we're starting with, now I want to use 3 sig figs here. I don't know why they have 2.4. Okay, so we're starting with sodium. We want to end up with grams of sodium chloride. Okay, well, how many, if I'm going to say I've got 2.4 grams of sodium, what does that constitute if I have a molecule of sodium chloride? Well, it's going to be the old molar mass, moles here again. We need moles of sodium. And sodium was, what was sodium? $22.99. And the ratio of sodium to sodium chloride is 1 to 1. And we want to end up with sodium chloride. Okay, so our grams cancel, our moles of sodium chloride of sodium cancel, and we want to end up with, oops. We want to end up with grams of sodium chloride. So we need a molar mass. And how many grams on sodium chloride? Let's see, sodium is $22.99 and chloride is $35.45, if I remember correctly. Okay, sodium is $22.99, chloride is $35.45. Okay. So cranking this baby out, we're going to get 0.40 times 35. All divided. Okay, so looking at 3.70. Now we have 3 sig figs, 4 sig figs, infinite sig figs, 4 sig figs. So my answer is going to be 3 sig figs, so 3.70. Grams of sodium chloride. Now that's a very useful kind of calculation. Okay, so do you see how we're using dimensional analysis from Unit 1, big time? Now, Chapter 7 is not a lot of math. It's more of a reaction kind of chapter. When we get into unit 5, though, we're coming directly back to this, directly back again. So I keep pushing this dimensional analysis in Chem 400, big time, particularly the first semester, particularly. When you take physics, dimensional analysis. If you take any geology, if you get quantitative geology, you'll be doing dimensional analysis. If you get into engineering, you'll be dimensional. So this concept of dimensional analysis, unit cancellation, is very fundamental. And that's why I'm spending lots of time going through these problems, doing unit cancellation, sig figs, all the time. Okay, I'm going to retire my voice. So I don't be rude to you guys anymore. Are these starting to flow?
Yes.
Okay,